All right. Hello, everyone. Thanks for coming out to our presentation. We are the design of an electric powertrain for a two-passenger ATV, and we are advised by Professor Sepapur here at TCNJ. My name is Chris Quinlan. I'm a senior mechanical engineering major. I am the project manager as well as the drive component lead.
My name is Jake Steffen. I'm the webmaster. I am also in charge of the power supply and controls.
Just a brief overview of our project. We'll be designing an electric power plant capable of propelling a two-passenger four-wheel drive all-terrain vehicle. And for this project, we do have two main deliverables, the first of which is to create a full-size design of the powertrain, and then also to construct a 1/6 to 1/4 scaled prototype of our design. And then for this full-scale design, we do have a couple of performance requirements. The first of which is that it has to be able to switch between front, rear, and all-wheel drive. The motors have to have a total power of 9 to 12 horsepower and achieve top speeds of 27 to 36 miles per hour.
So our main incentive or motive to do this project was the idea that electric is the future. We're seeing this to a lot of different ways, specifically the idea that electric vehicles are really being accelerated into today's market, and also within the collegiate competitions, the Society of Automotive Engineering, also known as SAE, they're really pushing the global effort to make collegiate competitions such as the Mini Baja competition. If you don't know what the Mini Baja competition is, it's basically a go-kart competition that a lot of colleges compete in, and they typically use these gas-powered engines. So SAE is really making to look that switch to electric drivetrains. We saw this as recently as in July of 2022, where the first electric Baja competition was held in India. And this same progression also shows that it will make its way to next to Brazil, and we predict within the decade to the US. Now, here's just another example of how really big these electric go-karts are getting. So these pictures are actually all the way back from 2019. Volvo, the car company, actually made their own Mini Baja, electric Baja vehicle. So on the left picture, you can see their one motor system along with their suspension. And on the right, you can see the whole schematic of what they were trying to create.
When we were going through the design process, we did have to consider a variety of constraints that apply to our project, and we settled on three key constraints. The first of which is that we had to consider the economic. Given that this product will eventually be within going to market or to competition, we had to consider the price of all of our components, as well as the long-term cost of ownership, as well as the cost of use when charging the vehicle. Following this, we then considered the environmental impact, which is one of the main reasons we're going to electric. In addition to this, we also had to consider the materials used, such as the materials for the batteries and the motors. And then as well, this is an off-road vehicle, so we had to acknowledge the effect of the ATV on the wooded landscape. However, this is designed to be used in a tracked setting rather than in the woods. Finally, we considered safety. And the main thing we could restrict as designers was the chance of electrical failure, so we took that very seriously. And then we also had to acknowledge that there is an inherent risk of off-road driving, and that future iterations of this would have to incorporate safety features such as roll bars and such. Following this, we had to consider certain design challenges, the first of which we had to design a user-friendly network of rechargeable batteries. We had to have a steady and safe power distribution system that was controlled through a robust control system. We had to make sure that all of our electronics were able to properly handshake with one another. Following this, these electronics had to be compatible with our 4x4 drive system. And then all of our components had to balance cost and performance. And then finally, that our design was manufacturable.
So here's a really simple breakdown of where the power is going through our drivetrain. We go from point one, which is our charging port, as DC power, to the onboard charger. Then that power goes right to the battery system, and that goes through the ESC, electric speed controllers, and the converters if we need to step down in that DC power, and then finally to each of the four motors for propulsion. Now, here's some of the really critical components for our full-scale model. The first one being a smart BMS, or battery management system, which does things like prevents overcharge, overheating, circuit shorts. It can also monitor the state of these batteries at all times due to its Bluetooth connectivity from any smart device. Next, we have our throttle, which just converts the physical input of your foot into the electrical signal. Next, we have our ESCs, or electric speed controllers, which just use the input signal to send any desired amount of power to each of the four motors, and they also alter the current sent to the motor to dictate that forward and reverse motion. And then finally, we have our motors, which just turn the electrical power and mechanical rotating shaft power. Now, given those components, here's a lot more in-depth breakdown of how the power is moving throughout this ATV. So one, it goes from your power grid plug-in to the onboard charger to your battery system. And from your battery system, you have one branch off to the BMS, and that also has a power cutoff point if it detects there's a short circuit or battery failure. And from that battery system, it goes right to the converter. And from that converter, you have two different networks. That first network is going to be each of your 4 motors, and that second network is going to be your throttle and also your controller, which sends a signal to the motors. And that controller also has a power cutoff point if the voltage is too high. Now, when we were designing the battery system for this vehicle, we had 2 different variations in mind. The first one being a competition build, which prioritized really longevity, a long lifespan. But with this comes a really increased cost. Then we are also considering a market or a competition vehicle, which would prioritize a low initial cost, but this would also reduce lifespan by a lot. But no matter what, through both systems, we had to make sure they performed high no matter what the design lifespan was. Now, just getting into some of these simple requirements for each of the 4 motors. Each of our motors is rated about 3,000 watts to 72 volts, which means that each motor needs about 42 amps at least to operate, and each of the 4 motors needs 168 total amps overall. Now, given each of those 2 considerations, we have 2 different battery designs for each of the builds. So the first one, the Cody lithium battery, is going to be for your market build. These, due to the fact that these are a lot smaller, you're going to need a lot more of these modules, but it's going to give you a lot longer of a lifespan. But because of that, the whole battery system will come out to about $2,400. But for a competition build, this would use more the lead acid battery makeup. Typically, lead acid batteries are really shorter in lifespan, but what this means they're a lot cheaper. So this battery system would actually only be $900 total, but again, this comes with a lot reduced lifespan. Now, when analyzing each of these 2 battery systems, it was important to us to really pick the right one. So we use a decision matrix for that. And you can see this decision matrix is for if we're building this thing to go into competition. You can see the grading scale reflects that, and that emphasizes cost over lifetime. So after going through criteria such as cost, weight, lifetime performance, and voltage drop. If you don't know what voltage drop is, it's basically the more power you draw from a smaller amount of batteries, the lower your operating voltage is going to be over time. So after going through each of those criteria, we found out that since we're building this thing to be put into competition, it would better, the Money Max lead acid batteries would be better for our system.
Moving on from our battery system, we'll now be discussing our drive components. So starting with our motors, we opted to go with 4 QSV3 mid-drive motors. These are each 3 kilowatt motors operating at 72 volts and drawing 42 amps. Like I said, these are brushless DC motors, and the key feature of these is that they have a 19 to 45 internal gear reduction, which gives us an output torque of 120 Newton meters, which we found was necessary in order to achieve acceleration that is competitive with other vehicles that are already on the market. And then each of these 4 motors will be controlled by a Voto controller EM100. These will be our ESCs for the full-size design. They have a working range of 48 to 72 volts and are able to deal with a max current of 100 amps, which is well within what our motors will be drawing. And then these will control the forward and reverse direction. So with all of these subsystems and components found, we were able to come up with the total estimated cost of the drivetrain alone, which came out to roughly $3,200, which while may seem high, we found that many vehicles that compete in the SAE Baja competitions are upwhere in the $10,000 to $15,000 range. So we found that if we leave the drive components at roughly $3,200, then that leaves plenty of budget for the rest of these subsystems to be designed in competition. Moving on from our full-size design, we'll now be discussing our 1/4 scaled model. And the purpose of this model is to provide a fully functional proof of concept for our drivetrain. And like I mentioned, this is a 1/4 length, width, and height scale, and therefore it is a 1/64 scale when it comes to weight and power. Just a brief overview of our design, we will be utilizing a MDF frame, as well as 3D printed suspension components with aluminum mounts for our motors. And then this MDF board will allow plenty of mounting space for all of our electronics.
Now just getting into some of the critical components for our scale prototype. First, we have our power source. There's 2 Rhino battery packs will be put in parallel to give us a total of 220 amps, each running at about 11.1 volts and about 4.4 amp hours. We also have a PDB or power distribution board, which helps easily distribute the power to each of the 4 motors. It has an input of anywhere from 8 to 60 volts and an output of 12 volts with a 280 amp max continuous discharge.
So then as far as the motor ESC combo that we decided to go with, we opted to go with the Onyx 260 watt brushless motor, which while this power may seem a little high for the scale, because we could not find a motor with an internal gear drive, we did have to up the power of the motor in order to achieve the same output torque that would match that of our full size design. With that being said, this motor has a working range of 4.5 to 13 volts, which gives us our varying RPMs for our drivetrain.
Now, one of the really critical components for not only our full scale model, but also for a lot of electric vehicles out there on the market is going to be your battery cooling. So for our design, we chose to go with heat sinks, which utilize heating fins through aluminum. So through this, we have 3 different cooling methods: convection, conduction, and radiation. And each of those methods gets used through, you can see the different holes on the bottom of the frame, along with the fins that go up, and they all dissipate that heat as the vehicle propels forward and dissipates that heat.
Moving on to our frame, as I mentioned earlier, we will be using an MDF 1/4 inch wooden frame. And now this fiberboard frame, we just needed to do a preliminary analysis to make sure that it could handle everything that we had to throw at it. So just under basic dynamic load testing, we're able to come up with a factor of safety of 14.2, which proves that this is more than strong enough to do everything we needed to. And then finally, the last thing we had to consider for our scaled model is the custom suspension system. And so this had to incorporate our 4 motors, which is why we had to design it ourselves. And it will be utilizing an A-arm suspension design that will be damped by shocks. And all of the structural components of this design are able to be 3D printed using PLA plus plastic. And the purpose of using 3D printed materials rather than aluminum or something maybe stronger is that it's able to be much cheaper and much easier to manufacture. Therefore, we were able to spend more of our budget on the electronics for our scaled model. With that being said, this will utilize 4 independent drive shafts that will connect the motor to the wheel. These drive shafts will pass through the hub using dry running bushings, which will balance that cost and performance requirement so it doesn't wear down the plastic of the hub. And then we'll just have an aluminum L bracket to support the motors.
Now, just diving into the budget to see what buildings like this, or what that would cost. You can see majority of the money, about 71%, is going towards our drive components. Majority of that is being each of the 4 motors, and about 12% to the batteries and their components, and about 11% to miscellaneous costs. And just a little bit more in-depth breakdown of each of the different components that we have purchased. Right now, we actually projected to finish about 65% under budget for what we approved for last semester, because we were able to definitely save a lot of money in different areas. So just in summary, our task at hand is to design the electric drivetrain for a 2-passenger ATV, with hopes that our findings and efforts will be fruitful to future senior project teams who are looking to make that switch from gas-powered engines to electric-powered drivetrains. We're also tasked with designing a proof-of-concept scale prototype that just demonstrates our calculations and projections will work effectively on a full-scale model. So again, we're designing an electric powertrain for a 2-passenger ATV team. That concludes the presentation, and I'll open the floor for any questions.
How far along are you in terms of actually building the corporate scale prototype? Do you expect to have a
So over break, we just finished up testing all of our electronics. They're all good to go. Right now, we're in the process of finishing up our suspension to the point where we can attach the wheels. And after that, we're scheduled to begin basic testing and driving probably in the 2nd week of April, and then completely done the design by the end of April. So.
Yeah, building off of that for the suspension, we do have like prototypes of the prototype suspension at a very low infill. And now at this point, the printer is just going to have to be running for a week straight, printing out everything. So, any other questions? All right. Yes, thank you all for coming.